Hi, my name is Junho Kim. In this video, I'll present our paper CPO, Chained Robust Panorama to-Point Cloud Localization. CPO is a localization algorithm that takes a panorama image and colored point cloud as input and finds the camera pose. Panorama images are beneficial for localization as the full 360-degree view provides the holistic scene context with less ambiguity. However, drastic scene changes can make localization challenging. An example is illustrated in the right, where furniture layouts in the query image have largely changed since the point cloud scanning. Given a query image and point cloud, CPO first creates 2D/3D score maps that reflect regional color consistencies and attenuate regions that possibly contain scene changes. Using the score maps, CPO first selects promising candidate poses, which are further refined with gradient descent optimization. 2D score maps assign higher scores to image regions that are consistent with the point cloud color values. To create 2D score maps, synthetic views are first rendered at various locations in the point cloud. Then, intersections are computed between the patch-wise color histograms of the synthetic views and the query image. Finally, for each patch in the 2D score map, the maximum histogram intersection is stored. Like 2D score maps, 3D score maps assign higher scores to point cloud regions that have consistent colors with the query image. To build 3D score maps, we reuse the patch-wise histogram intersections computed between the query image and the synthetic views. For each synthetic view, we back-project the histogram intersection values to the point cloud. The 3D score map is computed by averaging the back-projected histogram intersections. Now I will describe how CPO uses score maps for localization. For candidate pose selection, CPO leverages the 2D score map. Given a pool of translations and rotations, CPO renders a synthetic view for each pose and computes the patch-wise color histograms. The histograms are compared against the query image through weighted histogram intersection, where the patch-wise histogram intersections are weighed with the corresponding 2D score map values. Finally, the top K poses with the largest intersection values are selected for refinement. For pose refinement, CPO uses the 3D score map with sampling loss minimization. Given a point cloud P with coordinates X and color C, sampling loss is defined as the color difference between each 3D point's color and its projected location's sampled color. Here, the 3D score map is applied to weigh the color difference of each point. Using the weighted sampling loss, CPO optimizes each candidate pose with gradient descent. On the right, we show the optimization trajectories of the candidate poses. The candidate pose with the smallest sampling loss is chosen after optimization. Now I will briefly share the experimental results. CPO is tested on various datasets containing large amounts of scene change. Due to the 2D/3D score maps, CPO can robustly localize in these challenging scenarios. Here we show visualizations of 2D/3D score maps. On the left, new furniture and the moving person are introduced since the 3D scan, which are all attenuated by the 2D score map. On the right, we display the 3D score map, where the map places smaller values on regions near chairs and the blue carpet which are not present in the query image. In conclusion, we propose CPO, a robust algorithm for panorama to point cloud localization. CPO uses 2D/3D score maps that attenuate regions containing scene changes. Experiments show that CPO can successfully perform localization in scenarios with large scene change. Thanks for listening.